Bug algorithms. Simplest path planning algorithm is known as bug algorithm. Its names come from the algorithm is mimic how the cockroaches run around the kitchen and try not to get squished. And we have 0, 1, 2, and tangent bug. These are all just set of rules based on a minimum amount of information about the environment. And see if those rules led to the solution always find the goal or solution that find goal efficiently. Well, bug 0, known goal location, and we are now heading that location everywhere in the environment. Uh, if you're um, if you're blocked, it simply turns and follow that obstacle until there's no longer a block, then proceed to the goal again. Here we have a figure on the left. We start from the red dot and target the green dot, as you can see. Since it finds the goal location as Euclidean way it finds hypotenuse in order to proceed the shortest way, but in order to proceed the shortest way, but when the robot faces with obstacle, it follows that line, the line between the obstacle until the corners, until it finds a clear way to go that green right, the goal. In the figure at the right, in the figure at the right, we have another issue. So imagine that you have an algorithm that makes you turn one position when you see an obstacle. Imagine that you have a robot starting here and turn you're making a right for every obstacle hit. Then if you make a right, then you will go around all that obstacle. So if you make a left, then you will go here and then turn all the obstacle again. So that's a problem that takes time. And in some of the bug algorithms, you may never reach to the goal, but these are all can be developed by making um, development such as when you see another obstacle, you can um, create an algorithm that makes it turn another direction so you can fix it. Bug 1, the worst method, basically we are gonna follow every obstacle boundaries to identify them. When it sees an obstacle, it runs around the obstacle. We do a complete navigation of the obstacle until we return to the point we approached. Then it returns back to the closest point of the obstacle. As you can see here, we start from here and then from red dot, and then we turn around all the obstacle and we find the closest point. But even though we find it, the robot goes all around and then turn back to that closest point again, and it goes to the line that closest to the target, and then when it hits another object, it also navigates it that object too. This method is guarantee us that it will reach to the goal eventually. Um, in this method, we only know where the um, we only know our location related to the goal position. Back to there's another approach. So we know that we have a straight line that we draw between the start location and the goal location. This slightly more efficient algorithm, we have the both positions. So in the figure, once again we proceed to the first obstacle. Turn left when it hits the obstacle. Navigate around the obstacle until we hit our line again. Once we hit that line, we follow until obstacle shows up and try go back to it again. What I mean is we have that straight line in every obstacle. I mean every blocks that we that makes our line corrupted. That it tries to keep up in that straight line. So in the second image, as you can see here, there's a goal, and well, the configuration is reversed in here. The goal is here. The red, this is the green dot, and this is the red dot, which is the start point. And in here, if we make well, it would be left. If we make left in every obstacle, when we hit the obstacle, we make a left, then it makes a loop in here, and it keeps in the loop, and it never reaches to the goal. And these are all things that we can achieve with small developments in the algorithms, but this is how it works, and we will have example about this. Well, as you can see in here, we have this is the control panel that I made by PyQt, and we have the map in the example maps, and this is the map called house map, and we are now tracking it and tracking the robot in the RVS, and I'm now turning it to make sure it knows its location. As you can see, it's the it estimates the location pretty wrong in here because I have changed the some of the parameters, and that's why it makes too bad estimations in here. And now see, these are the parameters that you can figure in. I'm trying to see all those green dots to gather up so that it knows the location better. It estimates the location better. And now we will make a target set, and you will see that it will create a path for the robot, and the robot will try to follow that line. As you can see, it is not a really complex path, and robot will probably go as it is expected. As you can see, the position is slightly wrong, but it will eventually go to that target position that we just manually showed to the robot. As you can see, the target is now created, and the robot is following it. We can make that target in Node also. I'm gonna try and find that file. I made a Go target file, and give me a second. Well, here it is. Now I have find a position before, and I'm gonna show you the position parameters that I have set earlier. It is a location that the robot goes a bit harder. It's a hard position for a robot to go. It's 2 matters from X and 1 matters from Y. It's not like complex code. It just position parameters for and we are sending that target position. That the code is just it. Let's make a voice run. Sorry, I'm in the script file. Sorry. Okay. Well, once we set that go target, send that target in the go target Python file, then it will create another. You see, it will make another path planning. So it is coming back, but it is not right actually. Let me show you the gazebo image so that you can see more clearly. As you can see, there's no passage to go there. I'm sorry. Yeah, there's no passage to go there. It has to go back to the room in the room with the white table. Actually, there's no passage in that wall, but it goes to that way anyway. So the path planning algorithms are necessary. Otherwise, in using by using all those simplest path planning algorithms, it will um, make us lose a lot of time. So once it reaches to that wall, it will realize that it can't go to that target from that path, and it will make another target. So it will go from that wall, and then it will turn right, and it will keep making new paths to reach that target. It will update it until it reaches it.